Very good morning, everybody. First of all, I would like to introduce myself. Um, I'm Dr. S. Gowthaman from the Department of Engineering Technology, University of Jaffna, Sri Lanka. Today, I'm going to present on the influence of cementation level on the mechanical behavior of biocemented slope soil treated by surface injection. As we all know, the slopes are employed as the prime supporting structures of most of the transportation systems. So basically, if we take a slope, one of the major challenge is the stability of the near surface. The near surface is known to be the weakest zone in a slope, which is frequently defined as the mantle of the slope. Basically, since this near surface is in direct contact with the atmosphere, the zone undergoes a number of processes, including the deterioration throughout the time of the exposure. So particularly when the rainfall and snow melt occurs, the surface particles will be transported to the downslope. In addition, during the infiltration, as a result of the decrease in the matrix suction, there are a number of failures in the shallow surface zone. So this instability of this near surface poses challenges regarding the maintenance of earth structures. So the stabilization of the surface is crucial, and there are several methods available right now in the application stage. So some of the method I have listed here. So if you see these methods, the available methods have both benefits and drawbacks. For example, the vegetation is the eco-friendliest method. However, it takes quite a long time to achieve its fullest benefits. The methods like cement grouting, bituminous grouting, geosynthetic cover, they actually have a number of environmental issues. In particular, the synthetic chemical grouts, they are known to be hazardous and toxic material to the geo-environment. So it's very clear that there still continues to be a need to introduce new and reliable techniques to the field of geotechnical engineering. So basically, the biocementation is a novel and emerging sustainable technology in the field of geotechnical engineering. Basically, this method utilizes the biological substances and the mechanism is based on the naturally occurring process. Therefore, it is often entitled as a green engineering practice. The MICP, microbial induced carbonate precipitation, is the most promising biocementation technology. So if you see the mechanism, in fact, the number of bacteria are available in the natural soil. And some bacteria, they have the capacity to produce the urease enzymes. And this enzyme can catalyze the hydrolysis of urea and produces the ammonium and carbonate ions. In the supply of calcium ions, the calcium carbonate would precipitate. The calcium carbonate that is formed by the biological process is defined as the biocement and having the capacity to bind the soil particle and to increase the strength and stiffness. There are a number of benefits in the MICP technology. It can be implemented as non-destructive method, and also it's a less expensive and less energy consuming method. In addition to that, there are several unique merits such as retained permeability, easily controllable, and easily be healed. The purpose of this research work is to introduce this MICP as a novel alternative to the near surface stabilization. So in this paper, I'm presenting mainly the mechanical characteristics of the MICP treated slope soil. Basically, the MICP can be achieved at various levels of biocementation, which mean the percentage of calcium carbonate. And the objectives of this presentation is to comprehend the effective cementation level for near surface stabilization and to understand the physical and mechanical characteristics with varying cementation levels. Let's move to the materials and methods. So in this study, an erosion-prone expressway slopes located in Hokkaido, Japan has been chosen. Firstly, the preparation of bacteria. Following the identification and isolation of the ureolytic bacteria, the bacteria was cultured in the solid medium and then it was transferred to the liquid medium and produced the liquid medium as bulk for the applications to the soil. In this initial study, we have used the column specimen to demonstrate the expected results. So two-phase injection strategy was used here. In the phase 1, the bacteria culture was injected, and in the phase 2, the cementation solution, which consisted of urea, calcium chloride, and nutrient broth, were injected. Both the solutions were introduced at the surface of the soil columns and allowed to percolate under the gravity and capillary forces. The outlet kept open throughout the experimentation. There are a number of test cases. In order to achieve different levels of calcium carbonate within the samples, the different treatment durations were maintained. So accordingly, the treatment was performed from day 1 to day 14, as shown in this diagram. And at the end of the treatment, the given physical and mechanical characteristics were studied comprehensively. Moving to the results, firstly, the soil state. So as shown in this figure, we can see the untreated soil remained a loose structure. And when the treatment was increased to 1 to 3 number of injections, the specimens were still not well aggregated. When the injections was increased to 5, we could see a partially aggregated skeleton. However, when we increased the injection numbers above 7, a well-aggregated stable skeleton was witnessed by the end of the test. And also we could see that with the increase in the number of injections, the amount of formed calcium carbonate increases. In addition, there's a difference in the calcium carbonate profile in terms of the depth. We could see with the increase in the depth, the formation of calcium carbonate decreases, and which is mainly due to the filtration effect of the bacteria. Moving to the shear wave velocity results, when the shear wave velocity was compared with the rock characteristics, the light to moderately cemented soil specimen was found to be comparable with the stiff soil to soft rock material, and the heavy cemented soil specimen was comparable with the soft to hard rock material. So basically, while considering the appearance and also the physical state, the aggregate stability is the most important factor for the enhancement of near surface. Therefore, the heavy cementation levels appears to be more suitable and effective for the application purpose. Then the unconfined compression test. So from the test, we performed this unconfined compression test to all the specimens, and we found that with the increase in the cementation level, the peak residual strength and the initial modulus was increased, and also the failure strain was decreased. In addition to that, the response from the changed from strain hardening to strain softening. The shear test was also performed to all the different cases, particularly the case 7, 10, and 14 number of injections. So in each case, the 3 different specimens were tested at 3 different angles to have the different shear and normal stresses during the testing time. And based on the results, we could see that the friction angle increases with the average formed calcium carbonate content. And particularly if we see the peak state, the friction angle increased and the cohesion also increased. But when the specimen is moved to the residual state, we could see that there's a slight increase in the friction angle, while there's a significant drop in the cohesion value. So based on the observation, we could come to certain conclusions. The drop in cohesion indicates that cohesion is attributed to the particle connections, and the slight increase in the friction angle shows that the friction angle is attributed to the surface roughness. So moving to the permeability test, the permeability showed that with the increase in the calcium carbonate content, the permeability decreases. And finally, these are the conclusions of these presentations.